Now we are talking about the rates of reaction, okay, and how exactly different factors will be affecting the rate of reaction, okay. So let's talk about it. Look, whenever we talk about temperature, okay, so we are talking about it how exactly the rate of reaction will be affected when the temperature increases, okay. Always remember this, be it physics, chemistry, bio, or whatever, okay. Whenever temperature increases, the speed of the particles and hence kinetic energy of the particles increases, and because of which they collide more. If you notice, this whole chapter is about collisions only, yeah. Okay, so the more collisions, the more rate of reaction. And if you see over here, see, increases collision, increases collision, yeah. So whenever we have to talk about it, that the increase in temperature, increase in rate of reaction is happening, that technically should mean to you that increase in collision is happening, yeah. Okay, now look, when temperature increases, I've already told you, kinetic energy increases, because of which the particles' speed increases, and because of which the particles would collide more. Then we are talking about pressure. When pressure increases, so what would happen is this, that the volume is the amount of space something takes up, okay. So the volume decreases over here. So earlier, if it was this much, now it will become this much. And if you see over here, the particles earlier were very far away from each other, and now they're very close from each other, okay. They're very close to each other, and because of which obviously the collisions will happen even more, okay, and because of which the rate of reaction will happen even more, like the rate of reaction will speed up, yeah, faster. Then we are talking about concentration. Now look, concentration is all about how many particles are present in a particular volume. So over here, we take two beakers, let's say beaker A and beaker B. Okay, I've labeled it already. And in that, we are placing magnesium ribbon of, let's say, 5 grams. In beaker 1, we have only, let's say, 1% of, wait a minute. So let's say we have 1% of the HCl, okay, and beaker B, we have 10% of HCl. So if you see over here, we have only one particle, but over here we have 10 particles, okay? And because of which we can say that over here in beaker B, the rate of reaction will be much faster, because I'm pretty sure you said collision happened more, yeah? Okay, so the more particles, the more collisions happen, and the more faster is the rate of reaction then, right? Now we are talking about catalyst. Now what job catalyst has is, it reduces the activation energy, okay? So the activation energy lowers up. So for example, if you see these energy profile diagrams over here, yeah, okay, so what will happen is this, that this hump over here will be reduced, okay, all right, like that, all right, and because of which what will happen is this, that this much over here energy would be taken only to start a chemical reaction, and you will label it as EA cat in both of the scenarios. Please draw the line straight, because I'm drawing over here on the screen, maybe the line is a bit inclined, okay, but you are supposed to draw it straight. Use a scale to draw that. Now you see, earlier, let's say 2000 degrees Celsius was needed to do the reaction, okay, but now when catalyst is added, as it lowered the activation energy. If you have forgotten, activation energy is the minimum amount of energy needed to start a chemical reaction, okay. So if the activation energy is lowered up, okay, so now let's say this same reaction is happening at 800 degrees Celsius, yeah, okay, all right. Then over here we have talked about catalyst, and over here we have also talked about it, that it lowers the activation energy, and because of which the collisions will happen even more, okay. Now when the particles will reduce its size, okay, so let's say over here we look at this setup over here of beaker A and beaker B, okay, and if you remember, we have done the same experiment in the lab as well, yeah. So what do is, we place HCl in both of the beakers, and we add magnesium ribbon in beaker A, and we add magnesium powder in beaker B. Now the surface area is is decreased over here when it is in the ribbon form, and surface area increases over here when it is in the powder form. Now what is this surface area? Surface area is the amount of area exposed. So that means in beaker A over here, the acid is only exposed to the outer side of the magnesium ribbon and not inside. That means amount of time to reach the inner part of the magnesium ribbon, it will take a lot of time, okay, and because of which the rate of reaction will be much slower. However, in beaker B over here, the magnesium powder would be each surrounded by the acid, okay, and the surface area, since it is increased, because of which each particle is exposed to the acid, and because of which the rate of reaction is much faster over here. Okay, if you have any questions, please approach me. Okay, take care. Bye bye.